Imagine a bright crimson cascade pouring from white ice, a waterfall that looks like a wound on a glacier. It's real. And it's called Blood Falls. But here's the catch. Nothing living in plain sight is bleeding. In this video, we'll unpack 7 shocking truths behind that red water. From ancient trapped seas to microbes that eat rock, and one twist that makes scientists look to Mars. Stay for the last one. The final fact changes the whole story. In 1911, geologist Griffith Taylor stood staring at a red streak staining a blue glacier and called it a remarkable phenomenon. He sketched it and filed a report that puzzled everyone. Quick question. What would you think if you found a red leak on a glacier? Over the next century, expeditions returned, each adding tiny clues. That small discovery became the spark for decades of geology, chemistry, and microbiology research. And in a moment, you'll see why those early notes still matter. The dramatic red isn't hemoglobin, it's iron. Specifically, iron-rich brine hits oxygen, and rust-like iron oxides precipitate out, tinting the water deep red. Think of an old iron pipe left in rain. It turns orange-brown the same way. But here's the curiosity gap. How did so much iron get trapped beneath a glacier in the first place? Soon we'll trace its origin to a salty reservoir sealed for millennia. This is chemistry doing theater on an icy stage. Beneath Taylor Glacier lies liquid brine that predates human history, possibly hundreds of thousands to millions of years old. Picture a sealed soda bottle of seawater, locked under ice since the ice advanced. Isotope and salt measurements act like a clock, telling scientists this water didn't just come from last season's melt. In a moment, you'll hear the micro-story of how geologists age that water and why ancient changes every time new data arrives, keeping the mystery alive. Rust usually needs oxygen. So how does iron oxidize under a sealed, oxygen-poor glacier? Pattern interrupt. Chemical reactions we rarely see on the surface. Microbes and dissolved oxidants can produce similar reactions. And when that deep brine finally meets the atmosphere at the glacier face, a rapid oxidation paints the water red. Stay with this thread. Later, we'll reveal which microbes act like tiny chemical factories and why this reaction is both surprising and logical. Hidden life lives there. Microbial communities survive in absolute darkness, using chemical energy instead of sunlight. Imagine bacteria that eat iron and sulfur like we eat bread. They derive energy by oxidizing minerals, a process called chemolithotrophy. Curious? In a moment, you'll see why these organisms rewrite our definition of habitable environments, and how a tiny cell can power a red waterfall visible from space. These microbes are slow, ancient, and unbothered by cold. Their metabolic pace is a lesson in persistence. These microbes don't photosynthesize. They extract electrons from iron and sulfur compounds in rocks, essentially breathing minerals. Think of them as miners extracting energy from bedrock. That slow work gradually remobilizes iron into solution, so when the brine reaches the glacier front and meets oxygen, the iron precipitates out as red rust. Open loop. Later, we'll compare their metabolism to potential life on Mars and why scientists care about this very specific biochemical trick. Small microbes, big planetary implications. The red flow originates from a confined, pressurized pocket trapped under kilometers of ice, where pressure and salt keep water liquid. Picture a cellar sealed for eons. Geologically, that pocket is insulated and chemically isolated, which allowed unusual concentrations of iron and salts to build up. But here's the catch. Fractures in the ice or warming can open that cellar. Stay tuned. One of the later scenes shows what happens when the seal is compromised, and why that prospect alarms scientists. You might ask, how does water stay liquid at sub-zero Antarctic temperatures? Simple physics. Dissolved salts drop freezing points. This brine is so salty it remains fluid under extreme cold, like road salt keeping ice melted at winter's worst. But it's more than salt. A cocktail of ions and pressure stabilizes the liquid state. In a moment, you'll see how that brine moves through tiny cracks and why mobility matters for both chemistry and microbial survival. Because movement carries nutrients and spreads the red stain. Chemical fingerprints hint that this brine started as seawater trapped by advancing ice, then concentrated over millennia. Isotope ratios and specific ion signatures act like forensic evidence, pointing back to an ancient ocean connection rather than simple meltwater. Compare it to tasting a stew and guessing the original stock. Scientists use lab tastes to backtrack origins, but the plot thickens. Some data contradicts a pure seawater origin, and that contradiction fuels new research you'll hear about soon. When teams drilled and collected fluid in the late 20th and early 21st centuries, they found surprises. Unexpected sulfate levels, microbial DNA never seen before, and mineral assemblages that didn't match simple seawater models. One scientist described the first sample like opening a time capsule that refused to say its date. Curiosity gap. What did the DNA reveal about ancient lineages? We'll dig into the genetic surprises and why every new sample resets the clock on hypotheses. If microbes can thrive in cold, salty, iron-rich, oxygen-poor pockets on Earth, could similar niches on Mars support life? That question stopped being hypothetical when Blood Falls became an analog for Martian brines. Picture a hard, cold planet where subsurface pockets hide life-friendly chemistry. Suddenly, the red planet isn't so alien. In a moment, you'll see the exact chemical parallels researchers use to justify rover missions, and why one salty spring in Antarctica helps design Mars instruments. Extracting uncontaminated samples from under kilometers of ice is brutal work. Teams low-temperature drill, sterilize metal, and practice surgical sampling like field medics. One microstory. A team member spent 48 hours in wet gloves, threading sterile tubing while a storm lashed the tent, all to avoid modern microbes sneaking into ancient water. Open loop. Next, we'll explain how contamination could falsify claims, and what protocols guard against that risk, because one mistake can lead to a false discovery headline. Contamination isn't theoretical. It's the enemy of valid results. Researchers use triple sterilization, filtered air tents, and control samples to ensure modern organisms don't ride into the pocket. Imagine trying to keep a pristine museum artifact untouched while the weather rages. That's the level of caution required. Forward reference. Stay for a later scene about how one near miss taught scientists to rewrite protocols, and why that lesson matters for future extraterrestrial missions. Precision protects the truth. Climate change threatens to alter the dynamics of glaciers, potentially creating new outlets for ancient brines. If ice thins or melts faster, sealed pockets might vent, releasing iron-rich water and altering local ecosystems. Pattern interrupt. Imagine a century-old cellar left open to a modern storm. The contents spill and react. In a moment, we'll explore ecological consequences and the ethical debate. Do we want to disturb these ancient chemical systems or protect them as natural laboratories?